3 considered a simple design and a total of 2 bridges, one for testing where we could see where we could improve to gain the maximum outcome of the bridge weight pulling strength for our final design on competition day. The week later, the first bridge was a basic design which was thinly designed and contained a lot of supports within the beams. The bridge building design process was our group looking at various designs before we constructed the bridge. We then started by sketching the side view of the bridge and thought we would use our next design pattern with various spaghetti pieces to give it extra supports. We used a 1-to-1 ratio on paper which helped us cut the spaghetti pieces to size and then used glue to put together the design. We started with the sides of the bridge first and made sure they were identical, being the from left to right side of the road if this bridge was real. We then built the bottom of the bridge followed by the top and attached all sides together, which was then ready for testing after we weighed it. We were very lucky we found the time to make and test the first bridge before competition day because the way it was built, it was not long enough to fit on the sides. It was not long enough to fit on the sides of the testing apparatus, so we had to use 2 people to hold planks of wood on the sides so the width of the bridge would reach, which meant it would have been a lot more flimsy as it did not reach the minimal width design of 80 centimeters. We made the height of the bridge significantly high, which later on proved to not have meant a lot, as it mattered to the weight to resisting pulling strength ratio a lot more than the design and aesthetics of the bridge, which weren't really important in this task. The bottom beams of the spaghetti bridge were thick in terms of spaghetti stuck together to form one beam, which we thought would be all the support we needed, as the weight pulling force would pull mainly on this part of the bridge, although we were wrong. When the bridge broke at its maximum weight pulling capacity, it turned out to have split on one of the weak joints, which was not a thick column but one of the flimsy parts. This bridge was not very strong, considering it weighed 91 grams and resisted a weight of 9 kilos. Just before we held the bridge under the load-resisting plate, we discovered it would not fit through the bottom supports of the bridge, which meant that we had to make final adjustments before testing of the first bridge by cutting out small pieces of spaghetti which were in the way of the middle part of the bridge. This was a big help to us realizing all these errors, as it made our thought and realization process increase dramatically throughout the planning of the second bridge design. We figured before we started this project that it was essential to have a first bridge tested before competition day, and we would rather focus our time on doing that rather than making one masterpiece bridge design which looked good, as we knew this competition was not about aesthetically pleasing bridges but about which bridge with the lightest weight could resist the most downward pulling force ratio. In the second bridge, we chose to use strictly triangular trusses through the wiring design, which we acquired after more extensive research and design. It was a lot better to use than our previous X-truss design, as triangles are an engineer's best friend and there are no bending moments in triangular elements. Instead of gluing the entire spaghetti lengths together in strands to form one thick strand, we glued the strands together at intervals of about 5 centimeters. This proved adequate strength without adding excessive weight. We were then adding horizontal members on top of other members. We made sure we did not butt the joints up together to give no strength like we did in the last bridge, which was the cause of weak joints. We were sure to overlay them and then cut the excess away. For the second type of bridge, we decided to go for a more simplistic type of bridge and make the members thicker than what we made in the first bridge. That was a K-truss bridge. The bridge we decided on was a subdivided Warren truss bridge, keeping construction simple, being fewer members to construct, allowing for them to be thicker without going overweight. With the mistake of the first bridge being too short, we ensured that the second bridge would clear the span with approximately 25 millimeters on each side. The first stage of design was a sketch of the bridge to scale, ensuring that the correct span was achieved. The bridge was designed to have 100 millimeters high, hoping that with shorter members, the compressive forces would have less of an effort on the members. For the analysis, we calculated a load of 100 newtons, which is approximately 10 kilograms, being applied to the bridge. This design allowed for a symmetrical distribution of the load across the structure. The analysis shows that the diagonal members of the truss take a much greater load than the horizontal members. To decide the strength of spaghetti in single strand was held in position and weight was added at the center. Over a number of attempts, the spaghetti broke at 80.5 grams or 0.79 newtons. As the bridge will be of a 3x3 construction, we predict that the bridge should should have been able to exceed the 10 kilo load being applied in the centre. However, we did note that just because we are using an additional 8 strands of spaghetti, this does not mean that it would hold 8 times the amount of a single strand. If this was the case, 9 strands of spaghetti would be able to hold just over 7 kilos without the need of any truss designs. Also, helping to come to this conclusion was from the first bridge breaking around the 8 kilo of force. The bridge had a total length of 400 millimeters, which allowed for it to sit easily on the pads of the testing machine, which had a span of 350 millimeters. The mode of construction of the 2 bottom chords enabled the bridge to have a flat surface to sit evenly and distribute the load evenly. The bridge design did not have any cross bracing yet. The design was able to withstand any torsional stresses or twisting throughout the testing prior to breaking. The bridge failed in a total of 3 areas. The first area the bridge failed was in the center truss member. The second area the bridge failed was on the upper chord, and the final area the bridge failed was on the end truss, transferring the load to the testing unit. It was noted that during construction not all trusses were built as exact replicas of the other. There were slight differences in size, angle, and this may have had a contributory factor to the failure of the member transferring the load to the testing unit, as it appeared slightly longer than the opposite side that may have resulted in a loss of strength in the member. The second failure on the bottom chord of the bridge occurred at the connecting point of the spaghetti to ensure that the span was covered. This would have made it a weaker position on the bottom chord. It could be speculated that there was insufficient glue put in the location, as the connecting joint on the opposite side was undamaged. The upper chord again may have been a result of a slight difference in distance between the 2 upper sections of the trusses, as can be seen on the left-hand side of the figure. This would have made that section of the bridge weaker than the opposite side. As a result from the test, it is obvious the importance of having perfect construction to avoid any differences in strength that might arise, leaving weak spots in the structure. Additionally, to ensuring that the construction is appropriately aligned, connecting members between the trusses would have increased the strength of the design, as it would have been further evenly distributed throughout the design. What we learn on the final bridge is that using the maximum weight restriction provided by the rules doesn't mean everything, as our bridge weighed 107 grams and pulled 14 kilos. This is considered significantly strong. Having thicker spaghetti bracing pieces helped a lot. Having a thick bottom plate assistance to hold the pulling weight load was an advantage. Making a wider bridge was essential to the project, and the more time we spent on the bridge, the better the outcome was.